Okay guys, welcome back to this channel. So today we are going to be looking at um, fluid mechanics on metacentric height. So now, but today we're going to be looking at how we can derive, or how the process of metacentric height came about, and how the formula can be derived. So we're going to be looking at how to derive the formula for metacentric height. But first, we need to get the reaction, or we need to get the nature of a body when it's floating on a liquid. Now, for example, take this body which is floating on seawater, right? Now, like I said, this body will possess center of buoyancy and center of gravity. The center of gravity is actually the center of the body when it's on free air, when it's on the surface of the earth. But when it's immersed in a fluid, it possesses a new center of gravity which is called the center of buoyancy. So now, this is the center of buoyancy and this is the center of gravity. So when, for example, we assume the body is given a slight displacement. For example, let's assume the body is given a slight displacement. Now, when the body is given a slight displacement, right, don't forget this your center. Don't forget this your line of symmetry. It's called the center line. Let's call it the center line, which is possessing my center of gravity and my center of buoyancy, just like this. Now, when the body is given a slight displacement, there is a new, sorry. When the body is given a slight displacement, this line tilts at a certain angle. So you have your center of gravity here, and you have your center of buoyancy. Now, there's a new center of gravity, there's a new center of buoyancy that will be formed, which will be represented on a vertical line, let's call it B prime. So now the new center of gravity is formed. Now, let's assume, for us to get the formula of center of gravity, let's assume a strip. What do I mean by a strip? For example, let's assume a cylinder possessing some strip, a tiny strip of, we want to consider a small portion of that a particular cylinder, so that we can get, a small portion of a rectangular body, so we can get the formula for buoyancy. Now let's consider a strip. The thickness of the strip, let's assume it to be dx, right? That's the thickness of the strip. Let's consider the length of the cylinder to be L. Now consider this strip. We'll consider a smaller portion of the strip. Now when this body, this is the front elevation of the cylinder. This is the front elevation of the cylinder. The front elevation of the cylinder. Why this is the plan of the cylinder? So let's consider when this cylinder is facing upward, just like this, and it's given a slight displacement. Let's consider this to be the strip. Now when it's given a slight displacement, we'll be having something like this. There will be an area that will be formed when it's given a slight displacement. Now, for example, when it's given a slight displacement, there's what we call buoyant force. There's what we call gain in buoyancy and loss in buoyancy. This side experienced a loss in buoyancy because it came outside of the liquid, while this one experienced a gain in buoyancy. This one experienced a loss in buoyancy, and this experienced a gain in buoyancy. Just follow me step by step, you really understand where I'm going to. So now this strip, for example, this is a new center of, let's say this is a new point of buoyancy. And let's call it BB, and let's call this AA. Let's call this AA and let's call this BB. So now the height of the strip, for example, like I said, from here to here is the height of the strip, right? This is the front elevation. When you bend it like this, the thickness of the strip. Now this is the height of the strip. This is exactly what you are looking at. When I face this strip upward, the rectangular body is like this. This is the thickness of my strip. Why this is the height of my strip? Right? We are considering a small portion of this rectangular body. So when it's given a slight displacement, this will be my height of the strip, right? Now let's call this a slight displacement. Let's call this angle theta. Now if I bring this small portion of this particular cylinder out, we have something like this. Theta, and this is my height. Let's call this B, point B and point B. And let's call from here, from this part of this body, from this strip here to the center line here, let's call it O. And let's call it, it's having a distance S. From the strip here, from this portion of the strip here to the center line, of the rectangular body, we call it S. It's possessing a distance S. So the rectangular body here will have S. The distance here from here to the O, to this center line, we took out this small portion of this rectangular body, this small portion of this rectangular shape out. So this is point O, and this is S, and this is the theta, the small angle of displacement, and this is my height of this strip. So for example here, you know that since theta is a very little angle, a negligible angle, so we assume theta is equal to h over x, where from here the height of my strip will be given as x times theta. Right? Now follow me step by step. So first thing we need to do is to pick out, when I assume a small portion of my rectangular shape, or the small portion in the rectangular shape, then I pick out my strip out. So when it's given a slight displacement, it forms a particular area, or wear out a particular area. So taking out the rectangular portion here, I use it to calculate the height of my strip. So given the height of my strip, I have h is equals to x times theta. Now, since I've gotten the height of my strip, I want to calculate the weight of my body. Before I calculate the weight of my body, let me calculate the volume or the area of my strip. Now, given this particular strip here, it's having a length of L, it's having a length L, it's having a thickness ds. So you can tell say that the area of this particular strip here is given as L times dx. Right? Now, since we have gotten the area, I've gotten the height of my strip, let me get the volume of my strip. The volume of my strip, the volume of this strip will be given as area times h. Right? Now, since we got the h here to be x times theta, and we got the area here to be L times dx, so we can successfully put it here. The volume of my strip is equal to L times the x, that is my area, L times dx, and the h is given as what? X times theta. So this is the volume of my strip. So now the volume of my strip, which is L times dx times x times theta. Now we have gotten the volume of my strip. So now let's calculate the weight of this particular strip here. Weight of strip. To calculate the weight of strip, you know that weight density is equal to weight over volume, right? Or called specific weight. Specific weight is equal to, let's call this W. Weight over volume, right? And you know that specific weight is also equal to mass density times acceleration due to gravity, right? So if specific weight is equal to mass density times acceleration due to gravity, that means the weight of the body is equal to the volume times what? Mass density times acceleration due to gravity. So making the weight subject to formula from here, we have weight is equal to mass density times what? Volume, right? Mass density times acceleration due to gravity times volume. So putting it back into this place, so the weight of the strip is equal to mass density times acceleration due to gravity times volume. Now we know that the volume from what we calculated here is L times the x times theta. So we fix this back, we fix this into this equation. We have W is equal to density times L times the x times theta. Right? So this is the weight of my strip. Now we have successfully calculated the weight of the strip. Now what next do we have to do? Now if you look at this particular strip here, for example, let me redraw what I'm having here. This is the strip we are considering. This is the front elevation of the strip. Right? This is the front elevation of the strip. This is the center line of the strip. This center line, let's call this point O. So that from here to this strip here, it's having point O. And it's having a distance of x. since this is the front elevation of the strip too, is also having a distance of x, right? Now these are the same shape. So now this is the plan of the strip and this is the front elevation. Now we assume there's also another strip, so that when, for example, let's want to create a moment. So if we are having the weight of the strip here and times the perpendicular distance from here to the center point, now we assume since it's rotating at some point, a couple is formed, such that we have a force that is telling it to go this way, and also a force that is telling it to go this way. So that means we have two couples. Now, if you are considering a very small portion of the cylinder, which is a strip, we also assume there is also a particular strip here too, such that the weight of this strip will be acting opposite in direction to this other weight of the strip, so that a couple will be formed to tweak the angle or to tweak the shape of the body to a certain angular displacement. So for example, we're having another strip here, we're also having another strip here, also at a distance to the center line x. Now these two strips, the weight of these two strips will create a couple. This is weight 1 and weight 2, right? So now we're going to be taking the couple or the moment formed by one particular weight of strip. So now, if for example, let's take a moment towards the center line O. Taking moment of the weight of the strip towards the center line O, we'll be having, taking moment M, will be equal to weight of the strip times x, right? Now, given the weight of the strip to be this, we have what? Weight times the weight, which is this, we have mass density times acceleration due to gravity times L times the x times theta times x, right? Weight of the strip times x. So we have x times x here, we have mass density times acceleration due to gravity times L times the x times x, which is x squared times theta. Now this is the moment, or the moment created by the weight of this small strip to the center of the rectangle. So taking moment of the weight of any strip here to the center of the rectangle, this is what we're having. So since we are considering a small portion of the rectangle, which is a strip, now let's consider if we are to consider or to take moment of the whole strip. Now since we are considering a small portion of a particular of this particular body, to get the whole portion of the body, we have to integrate it, because that's exactly what we are going to be doing. Because differentiation, when we're considering differentiation, we're considering a smaller part of a particular object or a smaller part of a particular body. So when we integrate it, we are getting the whole portion of that particular body. So now let's integrate it. Let's consider the whole portion of the rectangular body. So to consider the whole portion of the rectangular body, we integrate it. So integrating density, integrating this, right? You have this times length times the x times x squared theta, right? So getting the whole portion of the moment of the whole portion of the cylinder, we'll be having, now taking this, because this is a constant, density times acceleration due to gravity, they are both constant. So take it out, we have density times this. We take it in front of the integral sign. Then we have length times the x times x squared the theta, right? So now we know that length times the x is what? The area, right? The length of the body times the area of the strip is what? The length of the body times the thickness of the strip, right? So let's call this times area times x squared the theta, right? Now let's leave this like this. Now we know that when that body tilts at some certain point. Now let me explain what I'm trying to say. Given that this is the body immersed in a fluid, the center of gravity and this is the center of buoyancy, right? And when it tilts, this is the center of gravity and this is the center of buoyancy. So when it tilts, we have a metacenter, right? Where the point where the new vertical line meets this other form of line is called the metacenter. So now, which will have a new center of gravity, right? At the displacement theta. Now, given this particular form, this particular displacement, Now we are saying to be that there is a new buoyant force that will be formed. Remember I said when a body is immersed in a fluid, we have the center of gravity and the center of buoyancy, right? We have the center of gravity and the center of buoyancy. On the center of buoyancy, the buoyant force will be acting, right? While on the center of gravity, the weight of the body will be acting. So on this center of gravity, we have the weight of the body acting. On the buoyant force, we have on the center of buoyancy, we have the force of buoyancy acting. So that the two forces are equal but opposite in direction. So now when we have these two forces, now when this is given a slight displacement, a new center of buoyancy is formed. From this point to this point, a new center of buoyancy is created. So that center of buoyancy, that's where the new force of buoyancy will be acting. So let's call this FB, just like we did here. So now this force of buoyancy will be said to create a particular moment. So let's take the moment of this force of buoyancy about this vertical line. So which will be the force of buoyancy times what the vertical distance, right? Which is from B to B. Force of buoyancy times vertical distance. That's taking moment of this. We have force of buoyancy times vertical distance, which is BB. So taking moment of this force of buoyancy, which is FB, F subscript B times B prime, right? Where B prime is the new center of buoyancy. So this is what we have. Now, taking this force of buoyancy, now BB, for example, let's take out this particular shape of triangle. Take out this particular shape of triangle. What are we going to be having? We're going to be having something like this. So that from here to here is BB. This is an angle theta, and this is M. Sorry, this is B prime, and this is B, and this is M. Right? We took out this triangle here. So such that BB is same thing as what? BM sine what? Theta, or BM times theta. So BM times theta is the same thing as what? BB. So we're having BM sine theta. Now because the theta we are considering is a very, very, very small displacement, so we just call it theta. So it's BM times theta. We have FB times BM times theta, right? So such that B prime is equals to BM times theta. BM times theta, that's taking the vertical component of BM we have, which is also equal to BB. So BM times theta is equal to what? B prime. So this is what we are having. So now what do we need to do? Since the force of buoyancy is equal to the weight of the body, or the weight of the whole body, and we have considered the weight of the whole body, or the moment of the whole weight of the whole body to be equal to this, right? And taking the moment, this is taking the moment of the whole body about O. Now this is taking the moment of the force of buoyancy about the center too. Now since the force of buoyancy is equal to the weight of the body, so we are actually saying the same thing here. So since the force of buoyancy is equal to the weight of the body, but opposite in direction, so let's replace it to the weight of the bodies. We have W times BM times theta, right? Now the weight of the body, since we got the weight of the body about a particular distance, now this is the moment of the force of buoyancy about BB. Now this is the same thing as also the moment of the force of the weight of the body about a particular center of gravity. So we're actually saying the same thing. So this can be equal to this. So with this now is equal to this. We have density times acceleration due to gravity integral A times x squared times theta. Right? Now theta will cancel theta, theta will cancel theta, right? So we are left with theta will cancel out theta, right? So we are left with weight of the body times Bm, which is equal to density integral A times x squared. Now we all know that the area times x squared is the second moment of area. We know that second moment of area is equal to what? The moment of inertia. So since moment of inertia, which is equal to the second moment of area, so we are replacing this now with the moment of inertia. So we have the weight of the body times Bm, which is equal to density times acceleration due to gravity. So taking the integral of A times x squared with the second moment of inertia, that's replacing it with second moment of area, that's replacing it with the moment of inertia, we have times I. Right? So now taking Bm to be subject to formula, we have Bm is equals to density times acceleration due to gravity, right? Times I divided by weight. Now, I'll tell you why we are making Bm subject to formula. Why we are making Bm subject to formula? Because we want to get the metacentric height, right? We want to prove the formula for metacentric height. You know that this is the center of gravity, this is center of buoyancy, right? And the metacenter is at this point. So to get the metacentric height, metacentric height is gm. So to get gm, we need to get bm minus what? Bg. Gm is equals to what? Bm minus what? Bg. Look at the distance here. The metacentric height to be m, and we are having center of gravity, and we should have center of buoyancy, right? If this is what we are having, we know that to get gm, which is the metacentric height, we need bm minus what? G. We need to get gm, we need bm minus what? Bg. That's what we need. To get the distance from here to here, we need distance from here to here minus distance from here to here. So bm is equals to what? So sorry, gm, which is equals to what? Bm minus what? Bg. So to get the metacentric height, we need gm, which is equal to bm minus bg, right? So this is why we are calculating bm. So when we have bm, we just get the formula for metacentric height. So since bm is equal to density times acceleration due to gravity times I divided by the weight of the body. So what's the weight of the body? We know that the weight of the body, we calculated from the beginning of the video to be weight, which is equal to density times acceleration due to gravity times what? Volume, right? And density times acceleration due to gravity, which is the weight density. So weight density times the volume of a particular body, give me the weight of the body. So substituting this formula into this equation, we have bm is equal to density times acceleration due to gravity times I divided by, substituting this into the equation as weight, substituting it in the denominator, we have density times acceleration due to gravity times what? Volume, right? So from this now we have acceleration due to gravity times density. We divide both sides from the top and the bottom. So we are left bm is equal to moment of inertia divided by volume, right? So now since metacentric height, which is what we are looking for, is equals to bm minus bg, then we can successfully say that we have gm, which is equals to bm minus bg, right? Bm, which is I divided as I, which is the moment of inertia, divided by the volume, we have I divided by v minus bg. So we have successfully calculated the formula for metacentric height. So that the formula for metacentric height is moment of inertia divided by volume minus bg. Okay, this is the metacentric height of a particular body. So where we can say bm is equal to I over v. Now, so thank you guys for watching. Please and please subscribe.